Hi guys, Sauce here. This is the third in a series of lessons using the integral to calculate volume. The previous lesson was the disk method. This is now washer method to help us calculate the volume of more sophisticated solids. In review, we used the disk method on a function similar to this. We had a piece of a function defined as a curve. We had endpoints, a lower bound and an upper bound. And we considered at first what would happen if we rotated the area under a curve around the x-axis. It would create a three-dimensional solid, and we learned to analyze how to find the volume of that solid. We chose any point in between the lower and upper bound. The function value at any one of those points represents the radius of a circle when just that line gets rotated around the x-axis. Here I'm attempting to draw in perspective one slice of the solid that gets created. And that slice is circular in shape. We call it a disk because it's a filled-in circle. And when we integrated all of those disk shapes, we added them up to create the volume. We used the integral. This shape can be represented in its own diagram as a circle, the radius of which is a value of the function. We could label the radius, in this case, f of x, if this was the f function. And to create the solid with the integral, we added up the areas that the radius creates by squaring that function value, multiplying by pi, and summing them all together with respects to x. We called this the disk method because the representative slice, the shape of each slice, even though they might be different sizes, is a disk. But what if we have a situation in which the area that we are rotating is quite different? We have area under the curve that we've studied before. And we also have the concept then of the area between two curves if we had two functions. In this case, I'm going to label one function g and one function h. And I can see that in this sketch, g and h cross one another. Pardon me. So where they cross, where h and g are equal in value, is a natural place to put some endpoints. And we can think of then the difference between these two functions as the area between them. And if we rotated this area around the x-axis, it would create a solid of a very different nature. What would the solid look like? Let's analyze it. If we take this point where the functions are equal and we rotated it around the x-axis, it would create a circle. It would not be a disk because this point is where they cross. There's no area under the curve or area between those two functions. So it would just be that point creating an empty circle. Likewise, in this chosen upper bound, if we rotated just this point, it would create a circle of a larger radius, but it would have no area because it's just a point that's being rotated. But what about every place in between? We could make a representative slice by imagining what happens when one infinitely thin line between these two functions is rotated around the x-axis. Well, let's make that representative slice in our perspective here by rotating the upper point around the x-axis and the lower point around the x-axis. And the line then that gets rotated is in between those two circles. I can shade it in to make a representative slice in perspective. This shape here ought to be analyzed separately in its own diagram, just like we did before. This shape is a larger circle with a smaller circle cut out of it. The area that we are going to add together and use an integral to sum up is then the area between those two circles. This is not a disk because it has a hole in it. We call this a washer, like the building material. And the circle that's filled in from the previous is called a disk. It just describes the kind of shape and the kind of slices that we're going to add together. Let's do a little bit more about this washer. If we're going to add up the areas of washers, and the washers are going to be created out of circles of a different size, because these functions have different values given any place in the domain, then it's worth doing a little bit more to our diagram to show us that the outer circle is going to have a radius that comes from the function value that is on top. In this case, this point that created the larger circle is a value that comes from the g function. G is on top at this point. So I can label that radius with a capital R, typically. Capitals mean the larger area, the larger radius. And then the smaller circle has a radius typically labeled with a lowercase r. And the smaller circle's radius comes from rotating the point that was below, and h's points or h's values will always be less than g in between the bounds that we've chosen, a and b. We've labeled our washer diagram. This is a representation of a washer, but the size of each washer, both the outer and the inner circle, are going to be different for every value in between a and b. So their radiuses, capital R and lowercase r, more precisely come from the functions. In this case, the top function for uppercase r is g of x, and the lowercase r is h of x. We create the area of the washer by taking these radiuses, squaring them, and multiplying by pi. And once we get the areas of the circles, we take the inner circle's area away from the outer circle's area to get the remaining shaded region area. So in general terms, if we are going to add up those washers, we do it with an integral. We find the difference between the two circles, the larger one being found by g of x squared times pi, and subtracting the smaller circle, which is found by squaring h of x multiplying by pi. These are each formulas for the area of a circle. And if we integrate with respects to x on the bounds from a to b, then this integral represents the volume of the solid that gets created by rotating this entire area between these two curves around the x-axis. What does that solid look like? I can finish my representation here by attaching the top circles, or the outer circle edge, just like I did up here, and visualizing how the inner circle edges would attach here to create a congruent region on the other side of the x-axis. This can be difficult to visualize, but it is a cup that has its middle hollowed out. It's a donut that has sharp edges at the top or bottom. We can use shading to try and capture the nature of that. This would be the inner edge of the inside of the hollowed out cup. So if this is going to work, we want to verify this general integral, which is the difference between the areas of two circles, all summed up. Then let's create an example and finish the calculation. Use the general equation to work a specific example. I am going to draw a difference between two functions. I'm going to choose a line and call this I of x, and that line will be equal to a slope of 1/2 times x, very simple line, and the root function. Let me graph this more precisely. If this tick mark is at 2, and we have 4 here, then the root of 4 is 2. So I know that my root function is going to hit that point there, and the root function that joins the origin will go like this. I'm going to call this function, the root function, j, and the expression for it will be radical x. With these two functions, I have an area between them that I can highlight with shading. If I rotated this region around the x-axis, a solid would form very similar to the example that we have here. I'm going to analyze this situation by drawing or attempting to draw the solid that gets created. This endpoint here that begins the area between the two curves is at 0 and has a value of 0 in both functions. So when I rotate it around the x-axis, it doesn't go anywhere, it doesn't create a circle, it remains a point. This point rotated around is going to be an empty circle because it's just a point. It has there's no line to create or sweep out an area. I'm going to do one representative slice. I could choose it to be anywhere. I'm going to choose an infinitely thin line, which is the difference of the values between the top function j and the bottom function I. I'm going to continue to analyze the solid that results by showing the endpoints of that line, each being rotated around, which creates then a washer of the difference between those two circle areas. I could do more if I wished to help me visualize how the solid gets created on the other side, and then we have an inside, which is a straight line, and use some shading to attempt to make it a little bit more three-dimensional looking. This here is on the inside. In this case, like a cup, we have a bowl, and the bowl has been hollowed out by a V or conical cavity inside the bowl. So we have a bowl created by the root function on the outside, but the bowl is hollowed out by a cone from the straight line function on the inside. We're going to do more. We're going to analyze a representative slice. The representative slice is a visualization imagining the solid sliced, if we could, like a melon, and then we take the melon and we look at the shape of the slice that results. It's going to be a washer, just like over here. A larger circle with a smaller circle cut out. The larger circle I could label generically as having a radius of capital R. The smaller circle with a lowercase r. But somewhere in this presentation, I want to be clear that capital R, the radiuses of the larger circle, always come from the function that is on the top in this presentation, which I've labeled J. It's the root function. Capital R's radiuses are going to be radical x. The radius is going to be different depending on where you are on the x-axis in the domain. That's why the radius is a function and not a set value. These washers are going to have different areas depending on where they are. Lowercase r comes from the inside circle, or the lower function value, which is the value of I, and I's expression is half of an x, or, put it more simply, x over 2. My bounds, A and B, my bounds go from 0, where the functions are equal, to, I've already labeled 4, where the functions are equal again here at this point. So the lower bound is 0, and the upper bound is 4. In some problems, we might have to calculate where the bounds are by first setting the functions equal to one another and solving for x. If I put 4 in for x, then I can confirm that the functions are going to be equal to each other. 1/2 of 4 is 2, and the square root of 4 is also 2. Now that I have my necessary information, I can use the general formula for the washer method to find the volume by integrating, adding up, on the interval from 0 to 4, the difference in these two circles. The first circle takes the higher function value, square root of x. That's the radius, and it creates a circle area by squaring that radius and multiplying by pi. I'm going to subtract the area of the smaller circle, whose radius comes from the line, x over 2, and making an area out of that, same way, circle, the formula for the area of a circle is I square that radius and multiply by pi. Integrate with respects to the x-axis. Now that I've created an integral, in this specific example, I can continue and finish by integrating my properties and evaluating, which we'll finish now. I can see that in the integrand, I could factor out a pi from these two terms, and because pi is a constant, I can bring it outside the integral and have it wait to multiply after I integrate. I'm going to do that. I'm going to factor out a pi from each of those terms and bring it outside the integral. I'm going to simplify algebraically these terms a little bit. If I've factored out a pi, then what remains is radical x all squared, which quite conveniently simplifies to x. And here, I'm going to think of this term after the pi has been factored out as x over 2 all squared, which will leave x squared over 4. But I'm going to think of that 4, dividing by 4 as multiplying by 1/4, so that I can separate out what I'm thinking of as a constant from the power that I'm going to need to integrate. This is still with respects to x. I'll continue. The integral of a difference is the difference of the integrals. Can't forget that pi is still hanging out to multiply the result. I'm going to make parentheses with a pipe because I'll apply the bounds from 0 to 4 after I find the antiderivative of these two terms. The antiderivative of x is x squared over 2, power rule for integration, and the antiderivative of x squared is x to the third divided by 3, and then multiplying by this constant 1/4. So I've got 1/4 times x to the third divided by 3, which I'm going to express as multiplying by 1/3. Let me slow down and check my work. Thinking of, again, integrating constant times the antiderivative of x squared is x cubed divided by 3 times the constant that was originally there. I'm confident, and I'm going to move forward by applying the bounds of integration. Pi is still waiting to multiply later. I'm going to put 4 in for x and get 4 squared is 16 divided by 2 is 8. I'm going to put 4 in for x here and get 4 cubed, which is 16 times 4, 64. It's worth using a calculator sometimes to check your work. Let me get one. I'm checking 4 cubed. I thought it was 64. Calculator agrees. Applying the upper bound of 4 and cubing it gives 64. 64 then is being multiplied by 1/4 and 1/3. That's the same thing as dividing by 12. I'm going to leave it as a fraction. 64 divided by 12. That's putting the upper bound in. Now I've got to subtract, and notice that I'm going to use parentheses again, because I'm going to subtract putting 0 in. This is going to wrap up quite nicely, because when I put 0 in, 0 squared divided by 2 is going to be 0, and 0 cubed is also going to be 0, so I'm subtracting 0 again. I've applied the bounds of integration. I'm going to ignore subtracting the difference between 0, so I'm left with this here, 8 minus 64/12. I prefer to convert the 8 to 12ths. So I get pi times 96/12 minus 64/12, and this will be 96 minus 64, 32/12 times pi. Might be helpful to reduce the fraction. I got it to this point. I like fractions. I don't feel they need to be reduced. This represents the volume of the solid that we're going to name bowl. This bowl was created by rotating an area between two curves around the x-axis. The representative slices that we sum together were the difference between two circle areas, which makes a shape similar to a washer. So we call this the washer method.